Hello, welcome to Physics Lesson 3.05, Part 2. We are going to continue talking about combining motion in two dimensions, so combining the horizontal and the vertical. And we have a little bit of a different format today because I'm going to be doing quite a bit of screen sharing with you. So let me go ahead and do that now. Whoops, do that, hit share. If life was like a Wile E. Coyote video, we really wouldn't have to worry about combining motion. And let's see if you can figure out why. We'll show a couple clips here. So Wile E. Coyote, when he falls, he always runs out into the horizontal, stays there for a second or two, and then drops down into the vertical. And so if this was real life, we would never have to worry about combining two dimensions. But in reality, our motion looks a little bit more like this. I'm going to be showing you a clip of the world record blob jump. A blob is this big air balloon that they put on water. They have a platform here where people jump off onto the blob, and there's somebody on the other side that gets launched. So this was the Guinness Book of World Records highest blob jump. Oops. All right, what we see here from his start point to the highest point and back down is what we call projectile motion. Projectile motion follows a parabolic motion, and this is just a beautiful example of it. One of the things we talked about in the vertical, when we talked about vertical motion, was well, before we talk about that, let's point out that we have both horizontal displacement and vertical displacement. So he's displaced in both the X and the Y direction. So this is a really good visual of two-dimensional motion. Now, when we handle it, how does one affect the other? That's kind of what we're actually after today. So we're going to talk about that. But before we move on, I want to point out something. Now, I know he's a little bit off here. He didn't start at the water's level, but you'll notice there's a little bit of he's not quite level, but we almost have perfect symmetry in this, especially here at the top where at this point his displacement here equals that, here it equals that. And these shots were taken equal times apart. So because he's not starting exactly at the water's surface, we have a little bit of disparity, but this is a great example of how you have symmetry in the vertical, equal times, equal places, with the exception aside. So how are these two related? How, when you combine the horizontal and the vertical, how does that work? How does one affect the other? Well, to illustrate this, we're going to go to yet another video. It's called a shoot and drop. We have one of these in classroom. If you were watching this in classroom, we would do this demonstration for you. So this device on one side launches a ball and on the other side drops a ball. So let me go ahead and let him show you the prep. Got a spring load. So what he's going to do then, he's going to launch from one side, he's going to drop the other. So what's your prediction? Which ball will hit the ground first? When you combine the horizontal and the vertical, does it change the motion versus dropping something just in the vertical? So that's the whole point of this. So take a second, pause the video if you need to, make your prediction. Which side's going to hit first? All right, let's see how it turns out. Were you surprised? They hit at the exact same time. So what's the implication of that? The implication is that there's something really odd at work here, because a lot of you said when you launch a ball off, it's going to have more velocity, it's going to go faster, and I think it's going to hit the ground first. Or maybe you thought because you're combining the motions, it'll take more time because we have two, and so the one that drops will hit first. Every so often somebody says, I think they'll hit at the same time. So if you figured that out, good job. All right, this is the part where we're going to switch to the dot cam. So I'm going to minimize this, stop sharing my screen, and hit pause, and we'll be right back. All right, I need to check my microphone here. Microphone. Okay, so hopefully my audio is okay. So we are now on the sheet. You guys should have this sheet in your packet. And we have here a parabola, example of projectile motion. And I want to draw in some velocity vectors. So we're talking about what's going on with velocity. So I'm going to, on my parabola. Now I'm going to do the same thing on the other side. Technically, vectors always start from the same point. So if I'm going to draw this velocity vector over here, I should draw it this way, but I kind of want to have a symmetry here. So all right, I'm going to draw one in here. And you'll notice, just like the guy in the video, they're getting smaller as I go to the top. And that makes sense because I start off, I've got this, very large, I've got a launch. So I've got a pretty big velocity. Remember, vectors should be proportional to, the length of the vector should be proportional to the magnitude. So as I go up, I get smaller and smaller. I'm gonna make these nice and thick. So I want to resolve these vectors into their horizontal components and into their vertical components. Usually, when we draw in, we go head to tail. I'm going to do these a little bit differently this time. I want to draw in the vertical, and I want to draw in the horizontal separately. Whoops, let's see. Let me make sure I'm doing this correctly. Yeah, this will work. So what I'm doing now is I'm resolving my vectors. So if I was going to go head to tail, I would draw them over, but I want to be able to see the horizontal and the vertical very clearly. So I'm going to do this like this. So if I take my initial velocity, I have, and that's not very dark. I'm going to pick another color to go over this. Does that help a little bit? You can clearly see what we talked about when we, so we're talking about the vertical first. Let's analyze the vertical. First of all, my velocity diminishes as I get to the top of the flight path. So we're starting off with a larger value, smaller, smaller, and then I'm smaller, I'm getting bigger, I'm getting bigger. The other thing is, at the top of the flight path, notice I don't have a velocity vector, because what do we know about the vertical at the top of the flight path? FP. My velocity is 0, but remember my acceleration is negative 9.8, or well, I should say, not in this case, if that's my coordinate system, it would be negative 9.81 meters per second squared. We actually know it's going to be 9.81 meters per second squared down. But here's where things get really wonky. Let's look at the horizontal. Now I don't have a ruler with me, so I'm just going to use my pen here. And you can see that this is about, what, a third of my pen cap, a third of my pen cap, third of my pen cap, third of my pen cap. Whoa, what's that all about? What's going on with the horizontal velocity, the horizontal components? Do you see it? Constant velocity, guys. So when I launch this, my velocity in the vertical changes, but my horizontal stays constant the whole way through. So maybe you noticed what I'm missing. You're like, wait a minute, well, what about here? Turns out, and this is my colors didn't come out quite the way I wanted. This is a regular blue. I need it to be about a third of my pen cap. So if I start it here, I need it to be about that long. At the top of my flight path, I have horizontal velocity. Constant velocity for the entire motion, including top of the flight path. Well, guys, what does that mean for acceleration in the horizontal? Did you say I don't have, if I have constant velocity, do I have acceleration? Yep. Nope. I have no horizontal acceleration. Maybe you're saying, all right, that's just weird. I gave you an explanation a while ago, and I said it relates back to the reason why free fall physics seems so strange is going to be explained when we talk about forces. And that's going to be in the next chapter, actually the next 2 chapters. Because gravity is the only force at play, once we launch this, we're going to find out that Newton's first law, a body in motion stays in motion. This is constant because there's no forces acting on it in the horizontal once we launch it. But in the vertical, we have the force of gravity, so we have changing in the vertical. So that's a quick explanation that we'll get into much more detail in the next chapter. So let's look at one last, I'm going to pause again, and let's look at one last example of proof for this. So, okay, I'm going to share my screen one last time. We're going to watch Walter Lewin. He is a physicist at MIT. And he does an experiment. And what's going to happen in this experiment is he has a cart on with a ball launcher. And so the ball gets launched vertically, but it also has horizontal velocity that's given to it by the cart moving forward. So if the horizontal velocity stays the same the whole way through, when we push this and we launch the ball, what should happen at the end? Make a prediction here. Okay, let's see what happens and let's see if your prediction was correct.
So here's the golf ball. I'm going to fire the gun now. Close. Close. Reasonably close. Well, since it's only reasonably close, perhaps perhaps it would help if we give it a little bit of leeway. There goes the gun. Here comes the ball. And this is just in case. Tape it down. So as I'm going to push this now, give it a push, the gun will be triggered when the middle of the car is here. You've seen how high that ball goes, so that ball will go. And depending upon how hard I push it, they may meet here or they may meet there. You ready for this? You ready? I'm ready. Physics works.
Okay, let me double check my microphone. Turn on mic. So as it turns out, the horizontal velocity stayed constant the whole time. That's the reason why the ball was able to drop back into the same spot as the cart. It never changes. The path of the ball horizontally never varies from the cart. Of course, vertically it did. It went up and came back down. So what are our takeaways? Our takeaways are that the horizontal and vertical components of two-dimensional motion live lives, completely independent of each other. They don't know the other exists. In the horizontal, it's constant velocity, no acceleration. In the vertical, we do have changing velocity, but our acceleration is constant at 9.81 meters per second squared down. So we're going to, in the next two or three videos, get into how do we apply this to projectile motion. All right, that is our introduction. Thanks for watching and have a good day.